have developed enough theory now to find all solutions of second order homogeneous linear ODEs with constant coefficients. Let us consider the ordinary differential equation y double prime plus p y prime plus q y equal to 0, where p and q belong to R, that is real numbers. Suppose e raised to mx is a solution of this equation. On substituting in this differential equation e raised to mx in place of y, we get the following. So here if we substitute e raised to mx in place of y, the double derivative will give us m square e raised to mx. Here if we substitute y is equal to e raised to mx, then we get p times m e raised to mx, and here we will get q e raised to mx equal to 0. That is what is written here. This implies m square plus pmx plus q equal to 0, because e raised to mx is not equal to 0, so we can cancel e raised to mx and we get this. So this is a quadratic equation in M. This equation is called the characteristic equation or the auxiliary equation of the linear homogeneous ODE with constant coefficient. So roots of this quadratic equations are minus p plus minus square root of p square minus 4q divided by 2. The two roots we denote by m1, m2. The case when we have real and unequal roots, namely the m1 is not equal to m2 and m1 and m2 are real. So this happens when p square minus 4q is greater than 0. In that case, one of the solution is e raised to m1x and other solution is e raised to m2x of this differential equation, and the ratio of the two solutions is e raised to bracket m1 minus m2 bracket close x. It is clear that this e raised to bracket m1 minus m2 bracket close x is not a constant function, so the two solutions are linearly independent. So the general solution of this second order linear ODE with constant coefficients is y is equal to c1 e raised to m1x plus c2 e raised to m2x, where c1 and c2 belong to R. What we have done to get the general solution? We have taken linear combination of the two linearly independent solutions that we have obtained. Next we consider the case of equal roots. We get equal roots of this quadratic equation when p square minus 4q is equal to 0. In that case, the root is minus p by 2. So we get only one root solving this quadratic equation, namely minus p by 2. So this will give us only one solution of the ODE, namely e raised to minus px by 2. But we want to find the other linearly independent solution also in order to get the general solution of the ODE. So we use the method of reduction of order. So there we have learned that if we know one solution, the other solution, namely gx, we can find by writing the second solution as vx times e raised to minus px by 2 and then determine vx. So here we want vx to be not constant. So the formula we had determined previously, the formula for vx is equal to integral of e raised to minus integral px dx. Here px is p, so we write p here, p constant, divided by square of y1, the one known solution, square of one of the known solution. So the known solution is e raised to minus px by 2. Its square is e raised to minus px, that appears in the denominator, and this is integrated with respect to dx. So in the numerator and the denominator we will have the same quantity, So these two cancels and you get integration dx. Integration dx gives us ax plus b. But for this case, we just choose a to be equal to 1 and b to be equal to 0. That gives us vx equal to x. So the second solution is what is obtained by multiplying this vx with e raised to minus px by 2. So gx is equal to x times e raised to minus px by 2. Hence the general solution is the linear combination of the first solution and the second solution. So the general solution is y is equal to c1 e raised to minus px by 2 plus c2 times x times e raised to minus px by 2. So it is a linear combination of these two linearly independent solutions that we had obtained. Here C1, C2 belongs to R. So only remaining case is the case where the roots are complex roots. Of course, the complex roots are not equal. So M1 is not equal to M2 belongs to complex number and they are not real numbers. So this case arises only when this quadratic is such that p square minus 4q is less than 0. P square minus 4q is less than 0. So in this case, we have complex solution. Let the complex solutions be m1 is equal to a plus iota b. Iota stands for the square root of minus 1 and m2 is equal to a minus iota b. In that case, e raised to m1x is equal to e raised to a plus iota bx, which is equal to e raised to ax, and we have e raised to ax multiplied by e raised to ibx. So e raised to ibx using Euler's identity can be written as cos bx plus iota sin bx. Here we get that the solution is a complex valued function which is not a real valued function, but we want the solution to be a real valued function. So we will obtain a real valued function as a solution from this. And e raised to m2x is e raised to a minus iota b bracket close x, which can be written as e raised to ax bracket cos bx minus iota sin bx, again by using the Euler identity for e raised to ibx. This again is a complex valued function which is not real valued. To obtain real valued function, what we do is we add this 2 and divide by 2. So if we add these two terms will cancel and we will get 2 times e raised to ax cos bx. We divide that by 2 and we get e raised to ax cos bx. So this is one real valued function which is a solution. To obtain the other real valued function which will be a solution, we consider e raised to m1x minus e raised to m2x divided by 2 iota. So e raised to m1x minus e raised to m2x will give us that these two terms will cancel and we will have 2 times iota sin bx times e raised to ax. When we divide by 2 iota, we get e raised to ax sin bx. Now in this case, we get these two to be the solutions. Are these two solutions linearly independent? For that, we just take the ratio of gx by fx. We get tan bx because sin bx divided by cos bx, and this tan bx is not a constant function. So these two solutions, namely e raised to ax cos bx and e raised to ax sin bx are linearly independent solutions of the given differential equation. So any general solution will be linear combination of these two linearly independent solutions. So the general solution is of the form y is equal to e raised to ax bracket c1 cos bx plus c2 sin bx bracket close, where c1 and c2 belong to real number. Next we will see some examples related to the differential equations of second order linear with constant coefficients, and we want to solve it with initial conditions. So consider this question: solve 4y double prime minus 8y prime plus 3y is equal to 0, comma, with the initial conditions y0 is equal to 2 and y prime 0 is equal to half. So the characteristic equation of this ODE is 4m square minus 8m plus 3 is equal to 0. This characteristic equation we had introduced in the previous slide. So this is a quadratic equation. What we have to do? We have to find the roots of this quadratic equation. You can easily compute the roots of it, and it comes out to be m is equal to 3 by 2 and 1 by 2. So the general solutions are easy in this case. They are, since m has values real numbers and they are distinct, so that means that the characteristic equation has distinct real roots. So the solution is e raised to 3 by 2x as one of the linearly independent solution and e raised to half x as another linearly independent solution. So the general solution is linear combination of the two. That is, the general solution is y is equal to c1 e raised to 3 by 2x plus c2 e raised to half x. Now we want to use the initial condition also on this and determine this c1 and c2. So we differentiate this solution of the given differential equation. When we differentiate, this 3 by 2 come in the front. So y dash is equal to 3 by 2 c1 e raised to 3 by 2 x plus this half comes in the front. So you get half c2 e raised to half x. So now we substitute the initial conditions in this equation. When we substitute x is equal to 0, we get y0 is equal to c1 plus c2, but y0 is given to be 2. So 2 is equal to c1 plus c2. Now in this equation, when we substitute x is equal to 0, we get y dash at 0 is equal to 3 by 2 c1 plus half c2, but y dash at 0 is given to be half. So we get half is equal to 3 by 2 c1 plus half c2. So we solve this system of linear equations, these two equations, and find out the value of c1 and c2. You can easily solve it and you can compute what is the value of c1. It turns out that c1 is equal to minus half and c2 is equal to 5 by 2. So we have determined the c1 and c2 here, and so the solution of this initial value problem, the unique solution of the initial value problem, is y is equal to minus half e raised to 3 by 2x plus 5 by 2 e raised to half x. Here we have substituted the value of c1 and c2 that we obtained here. This is the solution of this initial value problem. Next we have looked at another example of initial value problem based on second order linear ODEs with constant coefficient. Consider the differential equation y double prime minus 4y prime plus 4y is equal to 0 with initial condition y0 is equal to 3 and y prime 0 is equal to 1. The characteristic equation is, if you substitute e raised to mx here, whatever you get. So finally the quadratic equation that you get is m square minus 4m plus 4 equal to 0, but that is a quadratic equation which can be written as a square. So it can be written as m minus 2 whole square equal to 0. So This is the case where the roots of the quadratic equation is real and equal roots. So out of this we get only one linearly independent solution of the given differential equation, namely y1 is equal to e raised to 2x. But we have already seen how to find another linearly independent solution. We have to just multiply x with y1. So the other linearly independent solution is x e raised to 2x. So the general solution in this case will be y is equal to c1 e raised to 2x plus c2 x e raised to 2x, which can be written as bracket c1 plus c2 x bracket close e raised to 2x. We want to solve this initial value problem, so we have to substitute these initial conditions here. So first we find the derivative of this solution. When we differentiate, we get y prime is equal to 2 times bracket c1 plus c2x bracket close e raised to 2x, when we had differentiated e raised to 2x here. And when you differentiate the first one, keeping second as it is, we get c2 from here and e raised to 2x. Now in this two equation we substitute the initial conditions. So we substitute x equal to 0 here. So when you substitute x is equal to 0 here, this will be e raised to 2 times 0, which is 1 totally, and this is 0. So only thing which survives here is c1. So y0 is equal to c1, but y0 is also 3, so c1 is equal to 3, which we get. And here when you substitute x equal to 0, we get c2 from this quantity, and from this quantity we get 2c1. So 2c1 plus c2 is equal to y prime 0, which is given to be 1. So 2c1 plus c2 is equal to 1. So we substitute c1 equal to 3 in this and solve it, and we find c2 is equal to minus 5. So when you substitute this c1 equal to 3 and c2 equal to minus 5 in the general solution that we had obtained here, we get y to be equal to bracket 3 minus 5x bracket close e raised to 2x. The third example we are going to see is the following. Solve y double prime minus 6y prime plus 25y is equal to 0 with the initial condition y at 0 is minus 3 and y prime at 0 is minus 1. The characteristic equation is m square minus 6m plus 25 equal to 0. So we have to find the roots of this quadratic equation. So this has complex roots, and the roots are m1 is equal to 3 plus 4i and m2 is equal to 3 minus 4i. You can solve this and verify that these are the roots. So we know in this case what is the general solution. The general solution is y is equal to e raised to ax. So you remember, if this is a plus b iota, then the solution is e raised to ax, that is e raised to 3x, then bracket c1 cos bx. Here b is 4, so c1 cos 4x plus c2 sin bx, so c2 sin 4x. So this is the general solution in this case where the roots are complex. Now in order to get the solution of this initial value problem, we have to use the initial conditions. For that, first we differentiate this. When we differentiate, we get first just we differentiate e raised to 3x and keep the next term as it is. So we get 3 e raised to 3x times bracket c1 cos 4x plus c2 sin 4x bracket close, plus now we keep e raised to 3x as it is and differentiate the second quantity. So we get e raised to 3x bracket, here we get minus 4 c1 sin 4x plus here we get 4 c2 cos 4x. Now you substitute here x is equal to 0, we get this is 1, and then cos 0 is 1 and sin 0 is 0. So this is C1 we get from this expression. So y0 is C1. On the other hand, y0 is minus 3. So C1 is minus 3. Next we substitute x is equal to 0 in this equation. So when we substitute x equal to 0 here, we get 3 times, then this term will survive and this will be 0, and here will be C1, so 3C1 from this whole thing, and from this thing this is 1 and this will not survive, and here we'll get 4C2. So we get 3C1 from this whole quantity and 4C2 from this quantity, and this will be equal to y dash of 0, but y dash of 0 is given to be minus 1, so minus 1 is equal to 3C1 plus 4C2. So we substitute C1 is equal to minus 3 in this equation, then we get C2 to be equal to 2. So when we substitute C1 is equal to minus 3 and C2 equal to 2 in the general solution, we get the solution of the initial value problem, that is y is equal to e raised to 3x bracket minus 3 cos 4x plus 2 sin 4x.